Good morning, good afternoon, or good evening, depending on where you are and what time you're watching this. Could be any of those. Welcome to another video on the mechanics section of the Year 12 course. We're on Chapter 11 today. This video is designed to get you ready for Chapter 11, Exercise 11C, where we're going to have a look at how we can solve maxima or minima problems in the context of acceleration and kinematics using differentiation. So before we start properly, as ever, there's some warm-up questions to have a go at, 4 here in total. So pause the video now, try these questions. Once you've got the answers, press play and compare your answers against mine. So let's have a look at the solution to question 1. So question 1, we have this function here, f of x equals x cubed plus x squared minus x minus 1. We need to use a factor theorem to show that x plus 1 and x minus 1 are both factors of f. So first of all, to show that x plus 1 is a factor, what we do is we need to try the function of minus 1. So if we go minus 1 cubed plus minus 1 squared minus x, which is minus 1, and simplify this. If this equals 0, then we've proven that x plus 1 is a factor. So minus 1 cubed is minus 1, minus 1 squared is 1, minus 1 gives us plus 1, and then minus 1. So minus 1 plus 1 is 0, plus 1 is 1, minus 1, that gives us 0. So therefore we have proven that because f of minus 1 is 0, that shows us that x plus 1 is a factor by the factor theorem. That is a factor of f of x using the factor theorem. It's now the same idea with f of 1. So to show that x minus 1 is a factor, we try f of plus 1. It's always a function of the opposite sign to what comes after the x. So to show that x minus 1 is a factor, we try f of plus 1. So that's going to be 1 cubed plus 1 squared minus 1 minus 1. And that does give us obviously 0. That's 1, this is 1. 1 plus 1 is 2, minus 1 is 0. So therefore, in the same way, we've got that x minus 1 is also, we've got that x minus 1, apologies there, is a factor of f of x, again by the factor theorem. So now, part B, we need to sketch the graph of y equals f of x, labelling any points of intersection with the coordinate axes. We found 2 roots to this equation. We've shown that minus 1 and plus 1 are roots, but we've not found the third root. Cubics can have up to 3 roots, and so what I'd suggest we do here is we try and find the third root, and one way we can do this is by using polynomial division. So for part B, what we could do is divide this function by one of these factors. And so I'm just going to plump for trying x plus 1. And so what we could do is divide the function by x plus 1 and see what we get. So we're going to divide x cubed plus x squared minus x minus 1 by one of the factors we've proven, which is x plus 1. So this will give us no remainder because it's itself, it's a factor of this. So first of all, we're going to divide x cubed by x. X cubed divided by x is going to give us x squared. Then we multiply x squared by the dividend. So x squared divided by the divisor, which is x plus 1. So x squared multiplied by this gives us x cubed plus x squared. After multiplying the answer by the divisor, which we get here, The next step is we subtract. X cubed take x cubed is 0. X squared take x squared. I'm going to write this as 0x squared. I know it's just 0, but think about it in terms of x squared. We now need to remember something which people often forget to do. So after we do the subtraction stage, we need to remember to bring down the next term from above. And so afterwards, we need to bring down this minus x from above and rewrite it here. Next, what we do is we repeat the process. So we need to divide the leading term here by the highest power of x in this divisor. So we're going to divide this x squared term here by x. 0x squared divided by x, that's just going to give us 0. Next, we multiply what we get by this divisor. So 0 multiplied by x plus 1, well, that just gives us a big fat 0. Even though we've got 0 here, it's important to do it term by term so we don't miss out anything in between. Next, we subtract. So 0x squared take away nothing below it, that's just nothing. Minus x take away 0, that just leaves the minus x we had from above, because we're not taking anything away from it. And next, we bring down this minus 1 term. Whoops, that was a bit wrong. Hold on. Sorry. Very messy. So next, we bring down this minus 1 term. That's better. So we get x minus 1. Now we repeat the process. So we divide minus x by this x here. Minus x divided by x, that just gives us minus 1. But we multiply this minus 1 by the x plus 1. Minus 1 multiplied by this gives us minus x minus 1. Final step, subtract. Because we're subtracting exactly the same thing from itself, we just end up with 0, which is what we'd expect because, as we've shown earlier, x plus 1 is a factor of this. And so that shows us that this function here, x cubed plus x squared minus x minus 1, that must be the same thing as x plus 1 multiplied by x squared minus 1. Now, x squared minus 1 is in itself a difference of 2 squares. So that's x plus 1, x plus 1, x minus 1. So x plus 1 times x plus 1 gives us x plus 1 squared, and then x minus 1. Now we know the 3 roots. We've got a repeated root at minus 1 and the third root at plus 1. We now have all the information we need to do this sketch. Pardon me. So here we can now sketch this function. So we're going to have a repeated root at minus 1, so it's going to bounce at minus 1, as it were. And then there's going to be another root at 1. So we're going to have something looking a bit like this. We're also told to label all points where it crosses the axis. So where it crosses the y-axis, we can just sub in x being 0. So what we get here is just this minus 1 term. So it crosses y-axis at minus 1. And this function here, f of x, we've proven is the same thing as this. Question 2, we need to create a cubic function g with roots at x equals 1 and x equals minus 1, and a y-intercept at minus 2. Well, what we can do here, we can use the answer from warm-up question 1 to help us. From warm-up question 1, we had that f of x was x cubed plus x squared minus x minus 1, which we showed was exactly the same thing as x plus 1 squared x minus 1. And this crossed the y-axis at minus 1. And so what we can do here is transform f of x. So we've already got the same roots. We don't want the roots to change. We want g to have the same roots as f. It's got a root at 1, just as f of x did, and a root at -1, again, just as f of x did. The only way g needs to be different to f is the intercept needs to be at -2 rather than -1, which f was at. So what we can do is we can double the y coordinates of f of x. And so what we can do here is we can transform f of x by multiplying it by 2. So we could say that g of x is the same as 2 lots of f of x, which is 2 lots of x plus 1 squared and x minus 1, which if you wanted to do it in expanded out form, this would be 2x cubed plus 2x squared minus 2x minus 2. If you're thinking, how has he expanded that out in his head so quickly? I've not. All I've done is I've remembered what f of x was here and just multiplied each and every term by 2 to get this. And so we can say that g of x is either this in factorised form or this in its expanded out form. For question 3, we're going to use calculus to find the stationary points of the function g and determine their nature. So just to remind ourselves what g of x was, we said g of x could well be 2x cubed plus 2x squared minus 2x minus 2. Now we need to remember, at a stationary point, the gradient is equal to 0. So what we need to do is to differentiate the function and find out when that function is equal to 0. When we do that, we'll work out what the values of x must be at these stationary points. So if we do g dashed of x now and differentiate each term step by step, this one here, the 3 comes to the front and multiplies for 2, which gives us 6x. The 3 drops down by 1 power to power 2. In the same way, 2x squared becomes 4x, minus 2x becomes minus 2, and any constant term disappears. And so g dashed of x is equal to this. And that's going to equal 0 at stationary points. So what we can do now is solve this as we would any other quadratic. So if we solve this for being equal to 0, hopefully you can see here all terms are even, so we can divide through by 2. So we're trying to solve where is 3x squared plus 2x minus 1 equal to 0. Fortunately, this here is a quadratic which is particularly easy to factorise. And so if we just partition this 2x out by multiplying the 3 by the minus 1, which gives us minus 3, we can think what two numbers multiply to minus 3 and add up to 2. Well, those two numbers would be positive 3 and negative 1. So we can rewrite this as 3x squared plus 3x minus x minus 1 equal 0. We can also use a class ways to solve this using the quadratic function. I'll show you that in a second. Anyway, imagine it wasn't a calculator. Imagine this is a question where it would show every single step of your working. This bit now will factorise. So 3x squared plus 3x, we can factor out a 3 and an x. That'll leave us with x plus 1. Here, both terms are negative, so if there's a common factor of minus 1, then brackets, we could have x plus 1. And you should notice here, this bracket duplicates. So we can put the whole thing, we can put the 3x and the minus 1 next to this bracket, x plus 1. That shows us that the stationary points must be where x is a third and when x is minus 1. So the stationary points are at x is minus 1 and where x equals 1/3. Next we need to think about the nature. That doesn't mean if they're aggressive, if they're nice-natured. The nature of stationary points means, is it a maximum or is it a minimum? Simple as that. So we can find out this using a couple of main methods. The method I'm going to go for here is by taking the second derivative. Where the second derivative is positive, that proves that a stationary point is a minimum. Where the stationary point has a second derivative which is a negative value, that shows that it must be a maximum. So we need to take g double dashed of x. So if we differentiate g of x again to get g double dashed of x, 6x squared, that's going to become 12x, and this 4x just becomes 4. So now we can just input where x is minus 1 and x is a third. So the second derivative where x is minus 1, that's going to give us minus 12 plus 4, which is minus 8, which is obviously negative. And so because we have a negative second derivative where x is minus 1, that shows us that we have a maximum where x is equal to minus 1. Now, if it wanted the coordinates of this, we could just input minus 1 into the function g of x. And so when x is minus 1, 2x cubed would be minus 2. This here would be plus 2. So minus 2 plus 2 gives us 0. Minus 2 lots of minus 1. That gives us minus 2. So minus 2 gives us plus 2. And then minus 2. So that's going to be equal to 0. So it's going to have a maximum where x is minus 1. So that's going to be equal to 0. Likewise, g double dashed, whoops, bit of a slur there, sorry, g double dashed, where we have a third, that's going to give us 12 times a third, which is 4, plus 4, which is 8, which is obviously greater than 0. So because the second derivative gives a positive value at x being a third, that shows that where x is a third, we have a minimum. So we have a minimum point where x is equal to 1/3. And again, in the same way, we can calculate the coordinates if we are asked for the coordinates of this minimum point. So you can just take this function here and input a third. So let's just do this now quickly enough. So g is 2 lots of a third cubed plus 2 lots of a third squared minus 2 lots of a third minus 2, which is minus 64 over 27. That's if the question asks you to give the coordinates of these maximums or minimums. Next up and finally, we have question 4, Calculus Corner. So at time t, a particle P moves along the positive x-axis and has displacement given by s equals t cubed minus 4t squared plus 4t minus 1. Find the time or times when P comes instantaneously to rest. So this is going to be at rest when the velocity is equal to 0. Obviously. When something's got a velocity of 0, it's not moving. So it's going to be at rest when v is going to be equal to 0. Now, we need to make a leap of faith here and realise that from before, v is ds over dt. So we need to make that link. So what we're saying here, v being equal to 0 is the same as saying ds by dt is equal to 0. Because from the previous lesson, we should remember that v is ds by dt. So we need to take the derivative of this with respect to t. So differentiate each term 1 by 1. T cubed becomes 3t squared. Minus 4t squared becomes minus 8t. Plus 4t becomes plus 4. And the constant term minus 1 vanishes. So we need to set this equal to 0. So what we need to do first of all, I'd suggest, unless you've got a class whiz, is to factorise this. I'll show you just for cheating way of a class whiz, because I just remembered I did say I'd show you for the previous question how to use a class whiz and I forgot. So if you've got a dirty cheating mind, which there's nothing too bad about that with maths, if you can find a quick way of doing things, so be it. I'll show you how you can factorise this to get the solutions. I'll then show you the longer algebraic way if you want to be a Puritan. So we press menu, we go along to equation / func, press equals, polynomial, degree is 2 because we're trying to solve a quadratic equal to 0. Coefficient of the squared term is 3. Coefficient of the t term is minus 8. Then 4. Press equals. So the first root is going to be where t is 2. The second root is going to be where t is 2/3. I'm hoping some of you might be crying, well, why? How? Is that really the case? So I'm going to show you. This is just if you want to be quick or you want to press it in an exam, you need to use technology to your advantage, which is only the wise thing to do. Do remember you can use your class whiz to save your day in a lot of circumstances, as you can with this one. Anyway, imagining this is a question where you have to prove it using a algebraic method, for example. This could factorise. So we could do this by factorising. If we multiply the 3 by the 4, we get 12. So we can think of two numbers that multiply to give us 12, but add together to give negative 8. Those two numbers could well be a 6, negative 6, and a negative 2. So we want this to be set equal to 0 when the velocity is 0 and it's at rest. So we can factorise here from these terms a 3 and a t out. That gives us t minus 2. Then here, both terms are negative and are even, so we can factorise out a minus 2 and then t minus 2. So then factorise further into 3t minus 2 brackets t minus 2, and that's going to be equal to 0 when the particle's at rest. So therefore, it's going to be at rest when the first bracket is equal to 0. The first bracket is going to be equal to 0 when t is 2/3. Or it could be where the second bracket is equal to 0, and that's going to happen where t is going to equal 2. And that's the warm-up completed. So let's just draw a line under that and move on to the main course of this lesson. So the focus of this lesson and the exercise, which you're going to try after, is solving maximum or minimum problems in kinematics. So we're just going to get right into a worked example. So a child's playing with a yo-yo. So this is common sense to you if you grew up in the 80s, 90s or noughties. So yo-yos now are probably very uncool. I don't really know, nor do I particularly care. Anyway, Google.com, you can find many images of a yo-yo if you're so inclined. Anyway, I digress. This yo-yo leaves a child's hand at time t equals 0 and travels vertically in a straight line before returning to the child's hand. The distance, s meters, of the yo-yo from the child's hand is given by this equation here. First off, what we need to do for part A is to justify the restriction on t being between 0 and 3. So let's just confront this problem first. So let's have a look at this equation for s, and importantly, s is a distance. It's not a displacement, it's a distance. And a distance, by definition, is non-negative. So that's a big clue here. It's a distance, not a displacement. So if we just write s equals 0.6t plus 0.4t squared minus 0.2 t cubed, you should hopefully notice that this has a common factor of t in all terms, and also each term is even-ish. It's not even because these are decimal numbers, but we have a common factor of not 2, but 0.2. So I can factorise out a 0.2 and a t from all terms. This first one, 0.2 times 3, gives us the 0.6t we need. Here, we multiply the 0.2 by 2 to get 0.4, and the t by t to get this t squared. To go from 0.2 to minus 0.2, we multiply by minus 1, and to go from t to t cubed, we multiply by t squared. So this is a quadratic, but because the quadratic term here is negative, it makes it slightly harder to picture. Normally quadratics you deal with have a positive x squared or t squared or whatever. So what I'm going to do, I'm going to multiply this here by minus 1, and then to compensate, switch the sign of all of these terms. So this here is the same as saying it's minus 0.2t. Now we switch the sign of all of these. So that becomes t squared, positive 2t becomes negative 2t, and this 3 becomes a negative 3. So then we have minus 0.2t, and this here factorises into, we can have t plus 1, and then t minus 3. And so we can now picture the graphical sketch of this. So if we imagine s going this way, and t going along, this is going to have roots where t is 0, where t is negative 1, and where t is 3. But remember, the cubic term for t cubed was negative, so it's going to be a negative cubic, so it's going to have a characteristic curve looking something a bit like this. So it's going to be going down, up again for a bit, and then down to God knows where. That should have gone through the origin. I can't sketch for toffee, so hopefully you'll forgive me and understand what I'm trying to do. That's 0. This is where t is minus 1. This is where t is 3. Now we need to discuss this restriction here. So it leaves the child's hand at time t equals 0. So let's just talk about that. If it leaves the child's hand at t equals 0, then that's where we start the clock, as it were, for this example. If we're going to leave at t equals 0, then we're only interested in t being equal or greater than 0. Before it leaves the child's hand, God knows, maybe the child was eating lunch or going to the toilet, or maybe he was playing with his parents. I don't really care. It starts at t equals 0, so here in this instance, negative time, we don't care about, we don't know about. So we're interested in the time being greater than 0. Likewise, because we're talking about a distance, this here must be non-negative. You can have a negative distance if someone's in your hand, for example. The distance from your hand is 0, but you can't have a negative distance. You can have a negative displacement, but not a negative distance. So next up, we need to think about, between the time being 0, whereabouts is this going to be non-negative, positive or 0? It's going to be non-negative between 0 and 3 seconds. We can word this by saying something along the lines of, when t is greater than 3, s becomes negative. The distance becomes negative, which is what we're not interested in. So t has to be not greater than 3. Now we can piece these two bits together. So we've got that t is equal or greater than 0. We also have that t is equal to or less than 3. So putting these two bits of information together, we can now say, therefore, t has to be between 0 and 3. For part B, we need to find the maximum distance of the yo-yo from the child's hand, correct to 3 significant figures. So I'm going to just be a bit of a naughty person here and show you how to do this on a class whiz. Why? Well, it's nearly Christmas. Christmas is never more than 300 65 days away, or 366 if it's a leap year, and that's a scientific fact. You can Google that if you don't believe me. And years fly by. Anyway, so part B. Find the maximum distance of a yo-yo from a child's hand. Distance, we solve for S. The distance is going to be at a maximum when it's at a 0 velocity. So it's going to be furthest away when the speed of this yo-yo stops just before it returns to the child's hand. If you're not sure what this yo-yo business is, Google a video on YouTube or something. So it's going to be a maximum distance, S max, is going to occur when the speed of the yo-yo, which is ds by dt by the way, is equal to 0. So what we need to do here is we need to differentiate this with respect to time. So ds by dt this 0.6t becomes 0.6, 0.4t squared becomes 0.8t. The 2 comes to the front and the 2 drops by 1, so the squared becomes power 1. And 0.2t cubed, that becomes minus 0.6t squared. And we want to solve this equal to 0 when s is at the maximum. So you could factorize this. You could multiply through by 5 to get these into whole numbers, then factorize, use a quadratic formula, whatever. It could be done. But just to sort of push this class quiz on you a bit more, I'm going to show you how to do it using this. So, menu, go to where it says equation / func. You'd have to scroll along to get to this, press equals. Polynomial, so 2. Degree is 2. And then you can input this directly. And so be careful. This here, first of all, is a coefficient of the squared term. That's minus 0.6. So type in minus 0.6. Next, the coefficient of the variable term, which isn't squared. This here is 0.8. So type in 0.8, then equals. Finally, the constant term, this is just 0.6. And press equals. So the first root is t plus root 13 over 3. The second root is t minus root 13 over 3. So let's just see this again. So the first root is 1.87 seconds. And the second root is this one, which is minus 0.535 seconds to 3 significant figures. Now just remember what we talked about for part A, the restrictions on t. T is non-negative, so t has to be at least 0. So what we can do now is reject this root here. We're not interested in a negative time. We are interested in this one here. So to avoid any rounding error, for part B, I'm going to input the time into this function to work out the maximum distance away from this child's hand. The maximum distance is going to happen at this time, but I'm going to take a more accurate answer for this time to avoid any rounding error. So if I just go back now and think about what this time was. So this time was 2 plus root 13 over 3. What I'm going to do, I'm just going to memorize that, go back to the normal mode, type it in, 2 plus root 13 over 3. And that's what we had. So I've got this answer stored now in the calculator's short-term memory. So now I can use this answer. So S max is going to be 0.6 times 1.87-ish. Going to put dot 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 to show the examiner I'm using a naturally more accurate answer than the 1.87. Then plus 0.4 then this time here squared, and minus 0.2, this time again here, cubed. Now, because this value is now stored in the calculator's memory, I can just press this ANS button to get the answer exactly as it is. So now, if I do 0.6 ANS plus 0.4 ANS squared, ANS just means the previous stored answer, which is this time here, but to about 10 decimal places. We can then round off afterwards to this 3 significant figures, but never round off prematurely unless you want to suffer through some rounding error and potentially lose some accuracy marks which needn't be lost in the first place. So anyway, now minus 0.2, answer to the power 3. Press equals, and we get to 3 sig figs 1.21. And the SI unit for distance or displacement is going to be meters. Next up, after you've checked what a yo-yo is on Google, be thinking, does this answer make sense? One good thing about kinematics questions, if you can relate it to real life, they should make sense and be realistic. So an average person, if average is such a term, a really tall man is about 1.95 meters. So a typical person is normally, a grown-up, this is, about 1.5 to 2 meters, between 1.5 and 2 meters-ish. So 1.21, that's going to be quite a way. So if you imagine a child with its arm stretched out, that would go towards the floor, which yo-yos do. But 1.21 meters is in the correct order of magnitude. That could actually be right. If you had a yo-yo which has 10 meter length, that's not going to be right. If you had a yo-yo which gives you about a mile, you've made a mistake. So always check if your answer makes sense if you can. Anyway, that's enough of that example. Next, if you can please, try exercise 11C, Stats and Mechanics book, page 187, and try all those questions. These do come up in exams from time to time. In the next video or two, I'm going to show you from past papers examples on these types of questions to do with variable acceleration. Try this exercise, do your best, and let me know if you're getting stuck. Thanks again for listening, and you'll hear from me again in the next video.